Determinant. But what I want to look at today, I want to talk about some matrix stuff. That's what chapter 4 is all about, is matrix stuff. 4.3 talks about something called the determinant. Now, the determinant is just a number. Okay? That's all it is. For every square matrix, there is a number associated with it that we can calculate called the determinant. Now, what does it mean, do you suppose, to be a square matrix?
Like
2 by 2 or 3 by 3 or 4 by 4. Same number of rows as columns, right? So it's going to look like a square when you write it down. So for every square matrix, we can calculate a number called the determinant. Here's how we write that. It looks like, this is the way typically it's written, it looks like an absolute value. You have these bars surrounding the matrix, and when you see something like that, it means determinant of matrix A. Sometimes you'll see it written as a lowercase det. That's how our calculator does it. We'll get to that in a little bit. Calculating the determinant of a 2 by 2 matrix is really simple. All you do is you take the product of the downward sloping diagonal, so A times D, minus the product of the upward sloping diagonal, minus C times B, those numbers. Okay? So, for example, what would we get if we wanted to calculate the determinant of this 2 by 2 matrix?
-1.
Okay, and you're going to get that because you have what times what minus what times what? 1 times 7 minus 2 times 4 gives us -1. Good. Okay, that's all there is to it. Very, very simple. It's a little harder as you get into bigger square matrices, but very simple for a 2 by 2. So what's this one going to be? Just do it in your head. What are we going to get? Yeah, so 17, 21 minus 4. Good. No, there's a little more. Okay, now that's a little hard to see. Sorry about that. Here, I'll turn the lights off for a second. See if it's better. Well, maybe that's better. Okay.
Yeah, because it's the middle one too.
To do the, yeah, this one's a little different, right? To do the determinant, calculate the determinant of a 3 by 3, what you have to do is you have to recycle the first 2 columns. So we're going to take columns 1 and columns 2 and just write them again. So now it looks like I've got a total of 3 rows and 5 columns. Now what you do with this is we're going to calculate all 3 of the downward sloping diagonal products that fit. I could start up here at the 2 and scoot on down to the 6, start at the -3 and scoot down to the 1, start at the 4 and scoot down to the 2, but then no more of them fit in there, right? So we're going to add up the sum of all 3 of those downward sloping diagonals. Okay, so it looks like 2 times 0 times 6 plus -3 times 3 times 1 plus 4 times -2 times 2. And then I'm just going to subtract from that number that I get, I'm going to subtract the sum of all the upward sloping diagonals. So minus the quantity, 1 times 0 times 4 plus 2 times 3 times 2 plus 6 times -2 times -3. And I'll just turn all those into numbers, right? So I'm going to get, what, 0 minus 9 minus 16 minus the quantity, 0 plus 12 plus 36. And ultimately, I just get a number, -73 in this case. So that's the answer. Yes, sir? Mathematicians. Okay, so now I'm going to show you a shortcut, though. You can do this on your calculator very quickly and very easily. I'm going to show you how. No, we will not get to the lab today, so don't even think about it. It's not. It's really not that hard. Okay, so how do we calculate the determinant of a matrix, say a 3 by 3? Oh, and by the way, if we take even bigger matrices, the process gets a little more complex. So this can be a good tool for you. You just go, as you might expect, you just go to the matrix screen, and we're going to enter that matrix as matrix A. So edit, matrix A, we want to be a 3 by 3, right? Yep. 7, 0 for the second row, 1, -2, and 2 for the third row. So put that in there. Then we're just going to quit, get out of there. Okay, now how we do this, we go to the matrix screen, and this time we're going to scoot over and use the math menu. So hit the right arrow. Which one do you suppose it is? Number 1, determinant. Okay, now all I have to do, what do you think I do?
Second.
Yeah, good. I'm just going to put matrix A inside the parentheses. I'm taking the determinant of A. So second, matrix A, close the parentheses, hit enter. There it is. How about that?
Whoa, I don't even have to see the charger.
Determinant of matrix A is -89. Okay. In the math, it's in the math menu, matrix screen. Okay, got it? And we can check this and just make sure, yeah, -89 is our answer, no big deal. So here's something you can do with that. Now, matrices, I'll tell you, and I know it's hard to imagine how these things could be so useful, but they really are. We'll do one little application here. Another one that I can remember doing in college that I always thought was just amazing that it worked this way. If you want to calculate, let's say, the focal properties or the properties of a system of lenses. If you want to make a telephoto lens, like a zoom lens, if you ever look inside a zoom lens, it's really complicated. There's a whole bunch of little lens elements, and when you zoom in on something with a zoom lens, these little lens elements are all moving around independently, and they sometimes go forward and sometimes go backward, and it's all controlled. But it's pretty complicated. If you want to calculate, let's say I want to take an object, and I want to find out where the image of that object is going to be focused, because in a camera you want to focus it on the film, right? And that's if you're going to make an image on the film. If you've got a whole bunch of lenses in there, you've got to take the object and calculate where it's going to focus an image for each one of those separate lens elements. So I take the first element, the object produces an image, that becomes the object that's focused by the second lens, etc., etc., etc. It's very complicated. But you can take all those individual lenses and write them as matrices, their properties as matrices, and combine them into a single matrix that represents the whole lens system. And the determinant is it gives you an important feature or an important property of that lens system. So I mean, this stuff, we obviously can't do that right now. It requires some other, some optics and some physics and things like that. But that's out there. I mean, if you go into a field where you maybe engineering or something, you're going to see a lot of this stuff because it really simplifies a lot of the mathematics you normally have to do. Okay, we're not going to do anything that complicated, but we can do something a little simpler. We can use a matrix to very simply and quickly calculate the area of a triangle, of any triangle. It doesn't seem like a big deal, but if I just give you a triangle on the XY plane and tell you where the vertices are, that is not really simple. It's kind of a time-consuming thing to do. What if none of the sides are horizontal and none are vertical? It ends up taking a little bit of work to calculate the area of that triangle. I mean, you can all do it, but it's not just horribly simple, right? I mean, it takes a little something. Now, with a matrix, though, you can always find the area very simply. Here's the trick. If you take the coordinates of each of the 3 vertices and you write the coordinates on each row of a 3x3 matrix, so the first row is going to look like x1 and y1. Those are just the x and y coordinates of vertex 1. And then you always put a 1 in the third space there. So the third column of this matrix just ends up being 1s. And look, that's all it is. I've got the first vertex in a 1, the second vertex in a 1, the third vertex in a 1. If I take the determinant of that matrix and multiply by 1/2, that gives me the area. Now, the plus or minus there just means you need your answer to be positive. Because sometimes when you do this, you're going to get a negative result. But all you have to do, all that means is, if you get a negative result, just make it positive. Okay? Because it has to be the absolute value or the positive value of the answer that you get. And it's a great little trick. It gives you the area of the triangle really simply. So let's try one of these. Let's try this guy. So on your calculators, what do I do here to find this area? Go to matrix, second matrix, edit, Matrix A, we want it to be a 3 by 3, right? So what's the first row going to look like of our 3 by 3 matrix? No, no. Remember, it corresponds to the vertex, to one of the vertices. So it's going to be like, if I choose this one first, doesn't matter which one. I'm going to do x1, y1, then 1, right? So that's 1, 2, 1. So I just take those x and y coordinates in order. 1, 2, and then I always put a 1 in the third column. Okay? So there's my first row, 1, 2, 1. What might the second row be then? 6, 2, 1. Okay, and then third row, 4, 0, 1. Okay, 4, 0, 1. And then I can just quit. Okay, let's clear this stuff out of there. And I'll just take 0.5 or 1/2 times the determinant of that matrix, right? So I'll just go second matrix. Where do I go? Math, good. Determinant, good. Okay, and then we just go second matrix A, close parentheses. So it should look like that, right? And if I hit enter, I get the answer -5. So what's the area? Well, area can't be negative, so it's +5. Yeah. Okay, that's it. How about that? Okay, so that's 4-3. That's really all there is to 4-3. All right, so moving on. Okay, 4-4 has to deal with some other matrix things. 4-3 we talked about the determinant. In 4-4 we talked about identity and inverse matrices. No big deal. Now the way to learn this and the way to really understand this is to think about this, compare it to, or think of it in parallel with what you do with numbers, regular numbers, because it's the same idea. We're going to take some number stuff that we normally do, and it's very simple for us, and we're just going to convert that into a matrix method that goes with it. Okay, so what does an inverse mean in a math sense? What's the inverse of multiplication? Yeah, division, right? In math, when we talk about inverse things, there are things that undo each other. So multiplication and division undo each other, right? Okay, what does identity mean in a math sense? What's the multiplicative identity for real numbers? In other words, 5 times what would equal 5? 1. Okay, so 1 is our identity number for multiplication. Always, yep. Because 1 is the only number I can multiply something by and have it be the same, remain the same, preserve its identity. Okay. Now, here's an interesting question. What do we multiply to get the identity? So what I mean by that is 5 times what is 1? No, 5 times -5 is -25. What is it? 1/5. Yeah, right. What's 2/3 times what is 1? 3/2. Yeah. Okay, so now in math, we say that we're talking about the properties of multiplication. The inverse of a number just means it's reciprocal. Right? So you're always taking the reciprocal. So if I multiply 5 by its inverse, that's the reciprocal. Well, earlier we said that the inverse of multiplication is division, but isn't a reciprocal really the same thing as dividing by something? I could say 5 divided by 5 equals 1, but that's just the very same thing as saying 5 times 1/5, right? Does that make sense? Totally equivalent. Dividing by something is the same as multiplying by its reciprocal, okay? So this is how we might write that in terms of numbers. Now, in math, and this is a little peculiar, and this might seem unsettling to you at first, because sometimes in math we use symbols, the same symbol to mean different things. And initially, I can see why that's a little confusing. But it's always a matter of the context. Depending on what the problem is all about, you know which one you're dealing with. In math, when we write something like a times that means an inverse. So it's really not the -1 power, right? When you write something to the -1 power like that in that context, it always means inverse. So this literally means the inverse of A. A times its inverse always equals 1. Okay? In math, that just means it's reciprocal. Okay? Now, for matrices, it's going to mean something just a little bit different. So, same thing is true, though. Now, when we write capitals, we mean matrices. When we write lowercase, we just mean numbers. So if I'm multiplying matrix A times its inverse, I should get back 1 also. Okay? Or if I multiply the inverse of A times A, I should also get back 1. But with matrices, 1 by itself doesn't mean anything. That's not a matrix. I have to come up with some matrix equivalent of the number 1. And this is what they look like. We call it I, and it's I because it's the identity matrix. The identity matrix is going to come in different shapes and sizes because it has to change. The size of the identity matrix has to fit the problem that it's in. The identity matrix could look like this. This is a 2 by 2 identity matrix. This is a 3 by 3 identity matrix. But you notice that it's always got the same characteristics. It's got these 1s in a diagonal from the upper left to the bottom right, and everything else in the matrix is always going to be a 0. Okay? Now on your calculator, you can get these. You don't have to write these out. If you ever need the identity matrix or something, you can just go to matrix, math, and look at the 5th option is identity. So if I want to do notice the identity matrix is always square. It could have 2 rows and 2 columns, or 3 rows and 3 columns, or it could have 4 rows and 4 columns, or 6 rows and 6 columns, whatever you want it to be. So I'm going to put the number of rows and columns I want is the number I'm going to enter. So if I do identity 6, look what it does. It gives me a 6 by 6 identity matrix. Okay? 6 rows, 6 columns, but notice I still just get 1s in that diagonal and 0s everywhere else. Okay? So this identity matrix then, it serves the same purpose for matrices as the number 1 does for numbers. So any matrix A times I has to give me back A, right? Because that's what 1 does. When I multiply by 1, things stay the same. If I multiply 1 times A, meaning the identity matrix times A, I still get back A. Okay? And we could try this, but I guarantee it works. If I take this matrix, whatever, any 2 by 2 matrix times the identity matrix is going to give me the same thing back. In any order, I can multiply the matrix by I or I by the matrix, either way. Just like multiplying by 1. So how could we determine then, just first steps first here, how can I determine if these 2 matrices are in fact inverses? What would they have to do if they're inverses, if I multiply them? What would they have to equal? What do we say if I multiply something by its inverse? Has to equal 1, right? The matrix equivalent of 1, the identity matrix. So I could just check, couldn't I, pretty easily? What would I do then to see? Yeah, put them in and multiply them, and if I get back the identity matrix, they're inverses, right? Okay, so I just put, and maybe we can even skip this. I'd put that in as A, and I'd put that in as B in my calculator, multiply A times B, and if I did, I would get back the identity matrix. There's another way I could do that too, though, that I'll show you. Okay, I could just put in matrix A and ask the calculator to take its inverse and see if that's the same as B. So I can actually use the calculator to calculate an inverse matrix, and it's pretty easy to do. So everybody put this one in. I'll show you how. Do a second matrix. Let's edit A to be a 2 by 2, that 2 by 2. So first row is just 3, 1. Second row is 4, 2. Okay, and now quit. And if I call up matrix A, how do you suppose, whoops, called the wrong one. If I call it matrix A, how do you suppose I take the inverse of that? What button on the calculator do you think would do it? What was our notation for an inverse? Yeah, -1 looks like an exponent. That's it right there. That's the inverse button. So if I push the button, it's right in front of the matrix button, actually. So it should look like that. If I hit enter, look what I get. It actually calculates the inverse matrix. Now that's pretty slick, but it's a little bit inconvenient because those are written as fractions. Can I turn those into fractions? Yeah. How do I do it? Yeah, math, convert to fraction. Then I hit enter to convert that answer. Look what it does. It makes some fractions even. Okay, so I can see that that is B. So B is the inverse of A. Okay, how about that? Okay, so calculating inverses, no big deal on the calculator. I'm going to skip ahead a little bit. Now, here's why we're doing this, honestly. Well, the way I'll show you quickly how to calculate an inverse, but you can see right away that this gets a little bit complicated. The technique or the method you use to calculate the inverse of a matrix is this. Now, it looks bad, but it's not horrible. It's always just the reciprocal of the determinant. So 1 divided by the determinant of the matrix times this 2 by 2 matrix. Now, what did we do to this? We started here and we ended there. Look, we just took the two elements in the descending diagonal and flipped them, just interchanged them. So instead of A being at the upper left and D being at the bottom right, we flipped them. So D is upper left, A is bottom right. And then the other diagonal, we just multiplied everything by -1. Okay, and so if we do that process, that gives us the inverse. But honestly, you can just do that on a calculator because for bigger square matrices, it just gets more complicated. You can always use a calculator though. Okay. Now it's possible. It's possible that the determinant will give you back a number 0, but I can't divide by 0, right? And so that would mean, if it turns out that the determinant, AD minus BC, right? If that is equal to 0, then the matrix has no inverse. Okay? And we say it's a singular matrix, has no inverse. That can happen. I have a really slick trick for us to get around that, though. We'll get to not today. Well, I'm going to skip this, because you guys all know how to do this on your calculator. Now, the reason we're doing all this stuff is so we can solve matrix equations. Oh, now that last one, that's important. One I want to do here. Okay, what about that guy? If I ask you to find its inverse, do you even need to try? You know it off the top of your head? You might, actually. The answer to that one, we know immediately how that one's going to work out. Can you tell me? Is that going to have an inverse? It's not going to have an inverse. How come? Alex, how come? It's not square. Yeah. It has to be square. Because remember that in calculating the inverse, we had to multiply by the reciprocal of the determinant. And if we go back about 15 minutes, remember we said that determinants are numbers that we calculate for only square matrices. So therefore inverses, we can only calculate inverses of square matrices also. If it's not square, it can't have an inverse. Okay? So that one doesn't. It's not square, so it can't have an inverse. Done. Okay, now here's what we want to be able to do. We want to be able to solve matrix equations. This can be very, very simple. Just pay close attention to this, and this is something that's, if you don't get this, it looks complicated, but you can get this right now, and if you don't, it's really not a big deal. Here's how you make this simple. Compare it to how you solve for x in a normal equation. If a and b are just numbers, what do I do to solve for x there? It's a one-step equation, very simple. Divide by a, right? So that's all we have to do. If I have a matrix equation that looks like that, I just have to do the matrix equivalent of dividing by a. Now you can't technically divide matrices. That doesn't work. But what we can do, we said that dividing by something is the very same thing as multiplying by its inverse, right? So that's what we can do. We can multiply by the inverse of matrix A to effectively divide it away. Because my goal is to get that A off of the left side, right? So if I just do this, if I multiply both sides by the inverse of A, but now remember what we said earlier a couple days ago about matrices with multiplication. The order matters. Matrix multiplication is not commutative. Matrix A times matrix B is not the same thing as matrix B times matrix A in general, right? So I'm going to multiply from the left on both sides. Now, what does this mean? The inverse of matrix A times matrix A. What did we say happened if we multiply a matrix by its inverse? What do we get back always? 1. We get back I, right? The identity matrix. We get back the matrix equivalent of 1, and the matrix equivalent of 1 times matrix X is just X, right? Okay? So then that's how we always solve these things. Our one step, instead of dividing by A, to get X by itself in that original equation, we're just going to end up multiplying matrix B on the left, right? That's the one that's on the left side of the equation. We're going to multiply B by the inverse of A from the left, right? Does that make sense? I think I said left side of the equation. It's on the right side of the equation. But we're going to multiply B by A inverse from the left. Right? Let's try that. So what if I want to solve this matrix equation? Very simple, right? To get matrix X, it's a capital X, so it's a matrix. To get matrix X by itself, what do I do? Yeah, call this matrix A, right? Call that matrix B. I'm going to do the matrix equivalent of dividing by matrix A, which I can't do. Instead, I multiply from the left by the inverse of A, right? So all we have to do in our calculators is just enter this one. We're just going to call this guy matrix A. We're going to call that guy matrix B. And we already know that our answer is going to be matrix X just equals A inverse times B, right? I can just do that on my calculator. So let's try that. So I'll just go second matrix, edit. Matrix A we want to be just a 2 by 2. And first row is 4, negative 1. Oops. Second row is negative 3, 1. So there's matrix A, right? I go second matrix, whoops, not that, second matrix, edit. I'll edit matrix B to be this guy, right? I've already got it in there, but you know. The odds of that. Negative 6, 3, okay, is bottom row. 8, negative 5 is top row. Now I can just quit. And I'm just going to type in this answer. So I'm going to call up matrix A, invert it, right, push the inverse button, times matrix B. That looks right, doesn't it? Right, that's what I know it's going to equal, always. Hit enter. That's it. Okay, that's matrix X. Okay? All right, so that's really not a big deal. The last thing I want to show you is just kind of a fun little application. Encoding and decoding matrices, yeah.
Yes.
Okay, this is... Okay, so cryptography is the science of encrypting and decrypting messages. And this is a really big deal in the modern world because we do so much stuff digitally, and digital information is so readily available. I mean, if you buy something online, it's not difficult for somebody to intercept that transaction. And if you didn't have, if your credit card was just there, people could get your credit card and all your critical information very easily. But the way we prevent that is we encode and decode stuff, right? We've talked about, like, I'm sure you've heard the word encryption, because that's a big part of websites. If you have a commerce website that you're buying stuff, you always want to use an encrypted website. And you notice they'll have that HTTPS at the top. That S means secure, so it's always encrypted. And you want to use a browser, and they're all this way now. They didn't used to be. You want to use a highly encrypted browser, and it uses like 128-day encryption, so it uses really big numbers in the encryption process, so it's hard to break. This is a simple version of how you can do something like that. This is a really easy way to encrypt something that actually is pretty secure. Okay, so here's what you do. Now, if we want to write something according with a secret code, all we have to do is we're just going to assign a number to each letter. So A is 1, B is 2, C is 3, etc. Okay? Then we're going to use, the bigger the matrix, the more secure. We're going to use a really small one to make it simple. We're going to use a 2x2 matrix to encrypt this, to create a coded message. And then to decode the message, all we have to do is multiply the result that we got from that by the inverse of the matrix that we used to encode it. There's a little bit on this, yeah. Just some stuff at the end of the assignment. So here's an example. If I want to convert get help to, I wanted to encode that so the enemy doesn't know that I need help. All right, so I'm just going to turn each of these letters into a number. So if I just go through the alphabet, A, B, C, D, E, F, G. G is number 7, right? So G gets a 7, E gets a 5, T gets a 20. If I want to use a space, I'll just always make that a 0, right? The H becomes an 8, the E becomes a 5, the L becomes a 12, and the P becomes a 16. So I'm going to take that and I'm going to break it up into just little small 1x2 matrices. Okay? So I've got 1, 2, 3, 4, 4 1x2 matrices that form that string. Each of those I'm just going to multiply by some random 2x2 matrix. Now the person, if you're the spy that's in the field and I'm just trying to send you this message, you would have to know what this encryption matrix was, but you're the only one that would know. I would know and you would know. Nobody else would know. And so I'm going to use this encryption matrix to jumble up all these numbers into something that's not readable. All I have to do is I'm going to multiply each 1x2 matrix by that encryption matrix, by the 2x2 matrix. And if I do that, I get, in this first case, I get the answer, instead of a 7, 5, I get a 9 and an 11, which won't mean anything, right? The second one was a 20 and a 0. That's to become a 40 and a 60. Well, obviously, 40 and 60, I mean, there aren't even letters that correspond to 40 and 60. Yes?
I can multiply 7, 5, and 2 into 8.
Okay, because we can do this in our calculators. If I call this, for example, matrix B, the encryption matrix, I could just go through, I'll show you a really quick way to do this. It'll save you some time. This is kind of cool. If I, yeah, I could do this. I could take, let's make this one B, so I'll go second matrix. Actually, I'll make it A. I think they call it A in the book, so I'll make it A. Call it A. Okay, so matrix A, whoops. Second matrix, edit. Edit matrix A to be this matrix. 2, 2, 3, -1, -2. That's our encoding matrix. Okay, so I've got 2, 3, -1, -2. Okay, so there's matrix A. Let's go ahead and put this little guy in for matrix B. So we'll always do B times A. So I want this to be a 1x2, and it's going to be 7, 5. Okay, so then all I have to do is quit, and I'm just going to go matrix A times matrix B. Uh-oh. Whoa.
Oh, yeah.
Oh, I can do B times A, sorry. That's what I meant to do. Whoops. Whoops.
Remember?
Yeah, B times A. Because remember, that's B, and we call the encoding matrix matrix A. So B times A, okay? And look what we get. Okay, there's our 9 and 11, right? Now, if you have to do a lot of this could get time consuming, but watch this, we can make this really simple. All I have to do is go back to the matrix menu, and I'm just going to go edit B, and just put new numbers in, like 20 and 0. Okay, and then I'll just quit, and I'll just go up and grab that B, matrix B times matrix A, and hit enter. And then so now it's going to change, but if I hit enter, it changes it to the new answer. So I can do that every time. I can just go back and change matrix B, and then go up and grab the B times A and hit enter, and it'll redo that for me with the new matrix B. And so if I go through this process, here's what I'm going to get. I'm just going to end up getting a whole series of encoded matrices. And so the coded message then that we would send, whoops, just looks like that. It's just this string of numbers that would be nonsense to anybody that intercepted our transmission, right? That's not going to mean anything to them until they were able to decode it. Okay, so how do I decode one? Let's say that you got this message that we know, let's say we know this is our encoding matrix, right? So we have to find its inverse to decode it. But let's say we got this message. All we have to do is break that up into 1 by 2 groups. Can everybody see that? Okay. Find the inverse of this matrix, just using our calculator. And then multiply each of those 1 by 2 matrices by the inverse. So if we calculate the inverse, and we could do this very easily, what we would get is this. Okay? We'd end up getting, instead we get 1, 1, 2, 3 is the inverse matrix. So I'm going to multiply each of those little strings in our coded message by that inverse, and I get 8, 1 for the first one, and I get 16, 16 for the second one, and 25, 0 for the third one, etc. And if I keep doing this, I end up with this decoded message. So I'll just take all those numbers in order, and they look like that, right? Now I just turn each of those into a letter. So 8 is A, B, C, D, E, F, G, H. 1 is, right? 1 is A, 16 is P. I thought I was going to go through this bit by bit, but it just tells us, it's going to give us a message, and that was a top secret message that I didn't want anybody to know about. So, what's that? Yes. Yeah. Okay. Anyway, that's it. Yeah.
What do I do?